So we'll go ahead and get started. We have two sessions today, one before lunch and one after lunch, and that was a kind of feedback from last year, I guess, when we had everybody in one session. So trying to make these more intimate or whatever you like. We're going to go through the Multiphase FMB course is typically a little bit shorter, typically 3 hours. We'll see how much we do compared to some of the previous courses that we've had this year with in a kind of a similar fashion where we focused on PVT, bottom-up pressures, and RTA. There we had a lot of stuff going on in the software. There will still be a few things in the software, but it's going to be a little bit more show and tell, go through use cases and stuff as we go. So, but we'll try to touch upon both things today. Let me know if you don't see my screen. Hopefully you do. Just a quick reminder that the course is recorded, and the software exercises that we're going to go ahead and do today is not on your company domain. Everybody here has access to Whitson Plus, but if you would like to access the software to do the exercises today, go to courses.whitson.com, input your email, and use this password right here. And if you don't, or if you have any issues with logging in, send an email to support@whitson.com. Actually, not the hook. So just send it to support@whitson.com if you have any problems with logging in. Okay. So I'd like everybody to just go ahead and do that right away, so we're on the same page there. So just go to courses.whitson.com. You'll be prompted with this login screen right here, and then in this menu, you just put in your email, and here you put in the password, which is what you see, which will be, so the password for everyone is Whitson FMB 2023 star. So that's the password. So you email and your password, and just make sure that that you've logged in okay. Give everybody, a few seconds to do this. Awesome. And again, if you have any issues with this, just let me know. Perfect. Goodie. So again, go to courses.whitson.com. Make sure that you are logged in with your email there, so not your company domain, and use this password that is provided in the slide deck. It was also sent out an email about it yesterday. And if you need it one more time, I can just mention that in the chat. That's the password. Perfect. So that's easy. That's goal number one. Just a reminder, this is kind of a part of a course series we do every single year. If you have to step out, or if you haven't been a part of some of the earlier sessions, we do want to rewatch them. Everything is recorded. Also, if you wanted to be a part of kind of the virtual live session, you can always join next year because we'll be rolling these courses every year. So there's 5 courses, one on PVT and phase behavior, also 2 sessions there, one before and after lunch. We had one on bottom-up pressures, we had one on RTA, we have this on flow material balance now, and next month we have one on nodal. So Graham is going to be the teacher for that one. And we might add similar courses later and just have them rolling every single year. And we try to also update the content. So you'll see if you didn't do the course last year, or if you did it and you came, you'll hopefully learn something new today, because I actually learned something new when putting together the content. So that's just a little FYI. Also, for those that need these kind of course, call it certificates or whatever, for their PE certification, then just let me know after the course so we can get that sent to you. So what we're going to cover is related to the Multiphase FMB and Whitson Plus kind of basics. So that's everything from login and access, which we did right now. It's workflows related to just clicking the different buttons, be able to know kind of some of the key functionality. I think related to these features specifically, you need to know how to navigate the zoom properly. You need to be able to navigate the slopes properly. And there's also a bunch of different kind of hotkeys up to the right that you should be familiar with, that we have implemented actually based on feedback from these type of courses. We'll also go through general structure and functionality in the software, this course, like all the other courses, had like a focus on, the PVT course had a focus on PVT only. This course has a focus on FMB only. So we're going to focus on multiphase FMB and its linked recovery factor analysis. There is also another FMB approach in the software called for dry gases. The nice thing is that all the concepts here are basically relatable to also dry gases. The methods are really similar. The only difference is that the one is iterative, one is not. And you can even use the multiphase FMB on a dry gas well. So that's why we just keep it to this. We'll go through a few examples in the end. And we'll also go ahead and assume that all the inputs are correct, that our PVT, our bottom hole pressures, etc., is provided, and that it's correct in the examples that we're going to run through. But in the end of the day, we'll just be back to basics, and hopefully at the end of the day, you have a couple more tricks in your sleeve that you'll find helpful to know when it comes to multiphase FMB. And some of them are even, one thing we'll talk a lot about, and I'll mention it quickly, is like any type of FMB method, whether it's Agrivall, Bossingame, the material balance we're going to look at here, like they always assume full boundary dominated flow. So for a lot of these low, infinite acting, low permeability rocks that we're working on, you might apply the method in a period of time when you're still infinite acting or boundary dominant or transitional. So that would mean that you will get a lower estimate of your content and pore volume. There's a lot of these other items in the that the method is providing us in terms of calculations that's super helpful. So we'll go ahead and focus on some of those things as well and try to keep it practical. You also see that a few things are repeated many times, and if they're repeated many times, that's on purpose. So that we want to make sure that the key concepts are shown at least twice. Awesome. So the first thing that we're going to go through is kind of the basics of the flow material balance. So when it comes to the flow material balance, very important and different from kind of like RTA exercises is that flow material balance is only used for one thing. And that one thing is to estimate the contacted pore volume, or basically what we're be able to drain from one well. So the only data that goes into the exercise is data from one well. And we'll see how it works with multi-wells, but for starters, for one well. And you want to try to estimate of all the resource in place, how much are we able to drain from this one well? So for like a large conventional reservoir, the problems, it's not like it's different problems we work with in unconventionals. It's, number of wells, length of wells, where you're going to place the wells, etc. And you would like to be able to evaluate after you place these wells in the reservoir, I have so and so much resource in place, but this well, it's not draining, far from all of it. Should I place in another well in between the two already existing wells, and these sort of things. All the flow material balance techniques, they are, simply using a very simple graph technique. In the software, in our softwares, in some of the Cotera, I know there's guys from Cotera typically in these courses. EOG has like an internal tool as well. You'll see that in those tools that the flow material balance plots, they go up and to the right. In some other tools, you'll see that they go down and to the right. And the reason for that is that when you plot the inverse on the y-axis, like you'll do in these plots right here, you'll stretch out the late points, which for most of these wells, that will be when you're in boundary dominated. So it's easier to interpret the late points. And if you plot the inverse of this, what will happen is that you'll get this cluster of data points down here that might be for many people hard to analyze. So that's the only reason why we have it like that. In theory, you could plot the inverse, and maybe we'll even put in a little toggle to plot the inverse at some point in the future, if that's wanted by people. The beautiful thing with flow material balance is that it's extremely quick to run. So I always run it religiously. Depending on what flow regime my well is, do I use like all the results and whatnot? Sometimes it's more, it can be working as a guide, especially if it's early on. But the beautiful thing is that it's kind of going back to this concept that I always try to repeat in the realm of RTA, at least, is that it's very fast, but it's super accurate, especially the multiphase FMB. And it's better to be essentially roughly right, or it's better to be roughly right than precisely wrong. So it all goes back to this. And a little bit in a broader context of the workflow and the courses that we were trying to teach throughout the year, this multiphase FMB part that we're going to focus on is kind of this the first thing that we all many times do as long as we have PVT and bottom hole pressures, because that's actually the only inputs. And that's a little bit beautiful because you don't actually need the height of the reservoir. You don't need to know even the porosity or these sort of things. The only thing you need is PVT properties, its initial conditions, and its production rates. And that makes this methodology very, very beautiful. Also, which we'll touch upon later, the multiphase FMB doesn't require relative permeability curves as an input, which is even quote unquote more beautiful. So very few inputs to do something very fundamental and important. That's also why it's this close in the workflow. And feel free, by the way, like if you have any questions as we go along here, just either unmute or type the questions into the chat, and I'll try to monitor this as we go. Every course that I hold, and I know a lot of you guys that see some of the names, they've been like, oh, another course with this guy. But every course that I hold, when it comes to these concepts related to well performance, because I see people are so confused many times when it comes to just the fundamentals. And if you know the fundamentals, your life is actually pretty easy. The problem is if you're lacking the next two slides in terms of understanding, it can be really tough actually to do this stuff. So that's why I always, no matter what course it is, and every opportunity I get, I try to repeat these two slides, not for myself, but for you, like to emphasize it for yourself that this is a really nice framework to work with when you're going to, or before you're going to go ahead and analyze a well. So the first thing is related to flow regimes, and that's very important that you have a very, very solid understanding of flow regimes. And we'll talk a lot about this today because it's really relevant for any flow material balance technique. So when it comes to flow regimes, we bucket the flow regimes into three different buckets. The first one being infinite acting flow, and that ends as the pressure transit reaches one of the reservoir boundaries. Then we have the total opposite of that, which is what we call boundary dominated flow. Also what we call pseudo-steady state in school. That's what we learned about. If anybody did reservoir engineering in university, at least I never probably even heard about a shale well or a multifracture or something well back then. So this is what we learn about in school typically, also called tank-like depletion. And that flow regime starts when the well pressure response is affected by every single reservoir boundary. Not one boundary, not two, but all of them. And that's very, very important for the audience to know that that's actually a super strict definition. And for a lot of these wells, it can take years, even for modern wells, to be in 100% full boundary dominated flow. In between here, we have what we call transitional flow. So let's say we've seen one of the reservoir boundaries, but not all of them. Then you'll be in transitional flow. For many people, this is kind of the reason why you can see B factors on your ARBS decline that's higher than 1 but lower than 2 for a very long period of time. Obviously, if you're in boundary dominated flow, by definition, you need to be either at or below 1, else the integral of that rate will be infinite. So so that's kind of the flow regime in between there. We won't touch upon it, but it's important to have it in the back of your mind that can be a flow regime that even if you're out of end of linear flow, for instance, if you're still transitional, then there's some part of your reservoir that's still infinite acting. So by definition you're not in full boundary dominated flow. So these are your three different buckets of a well, And at any given point in time, your well is in one of these buckets. So when you open a well, one of the first things that you should have an opinion about is what flow regime is this well in. And it is actually not that easy as you think. There's some analytical ways of saying if you're infinite acting, transitional, or boundary, and there's some numerical ways of doing it. And probably to be really comfortable, I always have to run both of this, but that's more related to the RTA course. So that's the flow regimes, and that's the buckets in the world that we live in. And when it comes to RTA, which is kind of very related to a flow material balance technique, we derive two parameters, and those parameters is the A-root-K parameter, and the second one is your contacted pore volume. And the A-root-K parameter, you can only quantify that rigorously when you're in infinite acting linear flow, and the contacted pore volume, you actually need to be in full boundary dominated flow to say what this is on with certainty. What RTA and multiphase FMB has in common is that this value here to the right, this contacted oil in place, that value in RTA and multiphase FMB, and we'll talk about that later, if it's like quote unquote consistent, those values should be the same. They're trying to estimate this exact same number. They're just using it or doing that in two different ways. If you have a numerical model that is in full boundary dominated flow in Whitson Plus, for instance, you could take that numerical model, you could upload those wells as very easy as one button, as simulated production history. You could put that into your multiphase FME method, and you'll get exactly the pore volume that you put into your numerical model. So what is contacted of that pore volume. So you can test that even if you have history matched a well, you bring that history match into your numerical model, and you take that history match. You can even take those parameters that you history match that run and make it into a multiphase FMB, and you'll see the pore volume. As long as you do full boundary, this multiphase FMB method that we'll talk about today will give you exactly the same number. So the guy to the right there, contacted oil in place and gas in place, that's the common denominator between RTA and FMB. And to 100% emphasize the difference between the contacted pore volume or the stimulated rock volume and the petrophysical mapped volume, we always show this slide right here. So your petrophysicist will go out and say, we have a block of rock here, has a height, has porosity, has a saturation, and we get this petrophysically mapped resource in place. Let's say that's 50 million barrels of oil in place. Then we put 3 wells in there and we complete it. And then these 3 wells are able to contact, let's say they're able to contact 10 of these 50. And that's pretty common, actually. If you do these comparisons, there's been a lot of case studies throughout the consortiums where we've taken RTA results and we compare it to the in-place volumes. And typically we see a haircut here between the blue area and the gray area of around, typically it can be 20% or 40% of the gray area. So big haircut. In the blue area, you can actually get really, whatever you've been able to contact, in that blue area, you can get really high recovery factors. So you can put in, for low GOR oil, you can get 20% recovery factor, 25% recovery factor. The more volatile it gets, that number can be even higher. Okay, so you can get really high recovery factors in the blue region. But of course, when it comes to these recovery factors that we typically see being communicated, in the industry below 10, that's these recovery factors where you actually taken into account the fact that you have this huge unstimulated rock. So if it's a fifth, if the blue is a fifth of the gray portion, you have to take your recovery factor and just divide it by 5. And that's how you always get below 10. But that's very important that when you communicate recovery factors, and also when you use recovery factors to calculate an EUR from these type of techniques, you apply that recovery factor to the blue region, you multiply with the volume of the blue region, and that's how you get your EUR. Anyways, what does people call this blue area? We call it a bunch of different things. Some people call it the contacted pore volume. Some people call it the stimulated rock volume, and some people call it the drained rock volume or any other version of that. My main point of showing you this slide is that this is not the in-place mapped volume. This is whatever that well or a set of wells have been able to contact. Okay, and that's different. And that's very important for you to know, especially in the realm of a multiphase FMB. So what you'll see in the software once you log in, and again, if people joined late, the login information was sent in the slide yesterday. The password is provided here on the screen, also in the slide deck and in the Teams chat. Yeah, and you'll the only thing you need to do is to go to courses.whitson.com and you log in there. And once you've logged in, you're basically ready to rumble. And what you'll see in the software is that everywhere where we're doing this kind of analysis, whether we're here in a multiphase FMB method, the word contacted is in front of the technique. The same as in analytical RTA, contacted oil in place, same with numerical RTA right here. The word contacted is used on purpose, okay? So that's very, very important. Good, so I think we're all clear there. How do we quantify the contacted pore volume? We can do that in a bunch of different ways. It can be you just use the pore volume, but more commonly we use oil in place for oils and gas in place for gases. But in theory, you could use all of these interchangeably. And you'll see that in the software, if you go into multiphase FMB and you change one of these parameters, it changes all the other ones, and that's because they're related. And they're related by the pore volume itself and PVT properties. And if the PVT properties are given to you, that's just multipliers up and down. So all this stuff is the same, but it's kind of different. Awesome. What I'm going to do now is I'm going to just, again, to emphasize this thing about boundaries, I like to do that just to make sure everybody's on the same page here, that for a very simple geometry like this, a fracture that only has no volume beyond the frac tips or frac height, there is only one boundary. That boundary is is basically on the sides here. There's only one direction of flow, and we call this a one-dimensional model. And the number of flow regimes is 2 flow regimes. You go directly from infinite acting flow, and then you hit the boundaries at the same time, and you're followed by boundary-dominated flow. And even if you stack these guys up in a symmetry of element model, which is typically what we use in like an RTA sense, then you're still dealing with a one-dimensional model because all of the individual wells or models are one-dimensional and they hit the flow or the boundaries at the same point in time. So there'll be basically 2 flow regimes there. If we add volume beyond the frac tip, for instance, like we have here, then we have 2 boundaries. We have the boundaries on the side right here, and then we have a boundary out here. And to be in full boundary dominated flow for this model in the red region, I don't think you'll actually be probably in any given at least time where we humans are alive. But that is a relevant model in a lot of these plays, especially if you're a little bit more higher perm on a relative basis. But here for you guys, this is a 2-dimensional model, has 2 boundaries, and it has 3 flow regimes. It has first infinite acting flow, and then we've started to hit the boundaries here, and then you're in transitional flow, and then if you run this well out for forever, you'll be in boundary dominated flow. So we talked a lot about flow regimes, but I think it's very important. But just to sum up how the flow regimes can then evolve over time for a well, again, we emphasize that because flow regimes is an implicit assumption to what we're going to talk about today. That's the sequence of flow regimes. So you can have, if you take those 3 combinations, I think you can only have 7 different sequences of flow regimes. It's either infinite acting flow for the whole observed history, else it's infinite acting flow followed by transitional flow, else it's infinite acting flow followed by transitional flow, and then finally boundary dominated flow, as we saw now. Or you can have infinite acting flow followed by boundary dominated flow, straight in transitional flow, or straight in transitional flow and then boundary dominated flow, or maybe even straight in boundary dominated flow for some very, very high or for higher permeability reservoirs and also probably modern completions. And a little bit more simplified, that's what we're trying to show right here. Okay, so hopefully the flow regime thing, that you got a 5% out of that, because that's important here. And hopefully when we go to the next part here, you'll understand why. Yeah, so just stop me if there's any questions at this point, but hopefully okay so far. And again, if you are having problems logging into the tool, just let us know in the chat here. You just go to courses.whitson.com, so not your own domain. put in the password and username, and you should be in good shape. So what I would like everybody to do in the software right now is to go into this FMB course project. So you'll see when you go to courses.whitson.com, go to the FMB course project. And then I would like everybody to go there, click one time, and then I see all the hidden projects, but I would like everybody to go into that project called FMB course. We'll talk about that later. And at the top right, click add project, and just call it your first name and then FMB course. And I'll zoom in a little bit so you can see it. So just call the project name this. We'll go through all of this a little bit later. Once you're happy with that, you click save. And then once you made your FMB course, you click that FMB course, which is at the top, or FMB course project, such that you're in that project. And we're going to work through the examples in that project a little bit later. Awesome. Good for starters. While we are at it, I just would like everybody to, let's just add our wells real quick. So I'll just send a link in the Teams chat. If you click that link in the Teams chat, you will basically download a set of wells. You can also do it in the certification, but I sent it in the Teams chat here. If you click that, that will download on your computer. And inside of your project, in mass upload, and maybe some of you have done a certification before and used these wells, that doesn't really matter because we're going to focus on a lot of things not necessarily related to the data, because hopefully after this you're going to go ahead and apply it on your own wells. So you just mass upload it. You find the certification wells and you click save, and then you get those wells in there. Later in the course we'll create some synthetic wells and stuff together. Okay, so I'm going to repeat that one more time. I've sent a link here in the team chat. You go in and click that link right here, and once you do that, it will download on your computer, and then you just go back to the project here. You click mass upload once you're inside of that project, and you just click it here and find it locally on your machine. Awesome. I'm just going to try this up. Good. Awesome. So hopefully you have some wells now. I'll repeat it one more time before we do the exercises, but that's what we're going to use here a little bit later. So when it comes to the Multiphase FMB workflow in itself, I'm going to give you guys a quick crash course. It's pretty easy. It's speaking to my heart because it's drawing straight lines through data points. It is one of my specialties. Love to do that. Is it right though? That's what we need to develop, some physical understanding of the process and some very nice quality checks. And thanks to particularly Barry and Leslie, that's kind of developed that framework of things you need to check. And as I mentioned before, a lot of good stuff here that has, even beyond the pore volume activity. So the problem that the Multiphase FMB tried to solve is super, super simple, is that all multiphase models require rel sperms, but in reality, we don't have it. So, a few years ago, these two guys, and I've told this to many guys before, or as 3 years ago now, COVID years, they just go so fast. They said they've developed a method. It's full multi-phase, but does not require rel sperms, does not care about geometry, and outputs the contact of pore wall. And as I've told many of you guys before, we honestly thought that this was, this is way too good to be true. So it had to be some BS. So we went home and tested for hundreds and hundreds of cases. Hopefully we can do some cases together today where you know the answer, you're changing the rel perms, etc. And when you do that and compare the results, as long as you're in full boundary, the exercise gives you exactly the pore volume that you've been putting into your simulation model. No matter if you have low fracture connectivities, pressure-dependent permeabilities, all these different artifacts that you can make the model more or less complicated. And what is multiphase, by the way? Well, multiphase can be 3 phases flowing in the reservoir. That's probably when it's the most important, but also if you only have water and gas, or if you have water and oil flowing in the reservoir, that's by definition strictly also a multiphase FMB technique. So we know the methodology works now. At least when you compare it to the most rigorous things you can compare against, which is these numerical simulation models. They do not require oil pumps, outputs the contacted pore volume, and do not care about geometry, which is huge. So it doesn't care about if the reservoir is a tank or a star or a square or a rectangle or a triangle or whatever. So that doesn't matter. But it assumes boundary dominated flow. And that's what I talked about before. That is an inherent assumption in any of these flow material balance techniques. And if you think about it, it makes sense, because the objective is to find how big is my tank. That's the only thing you want to try to do. How big is the tank that I'm draining from? But if you're in a flow regime that by definition haven't seen every single boundary of the tank, you can't say what it is. It's like if you're asked to, with your visual eyes, in a sense, you walk into a room and you're only allowed to look in front of you and to the side. Nobody expects you to say how, give you a very good estimate of how big the room is when you haven't seen the walls behind you. The walls behind you can be, just behind your back, or it can be 100 meters behind your back. So in that setting, you're kind of still in this infinite acting transitional flow regime. You might have seen a couple of the walls, but not all of them. So it's not fair to be even asking you that question. But you can give a minimum estimate of how big the room is, because you see in front of you, it might be a couple meters, and to the right, so we know it's at least, I don't do kind of square feet and stuff too good, but you know what I'm getting at. Okay, so that's kind of the challenge with the multiphase FMB method, or with any FMB method when you're dealing with these very low permeability systems. Okay, so in practice, you use it a lot to bound your RTA work, especially on the low side. If you get anything lower than this, it's wrong. So it's very good, especially when you're working with bad data. And sometimes you have had enough time such that you use it to say with certainty that you're in full boundary dominated flow. The diagnostic plot is super simple. We plot a line on a curve. The inverse of that is your pore volume. This is a small OIP, big OIP, and bigger OIP. Inputs are PVT, rates, and bottom hole pressures. Nothing else than that. That's also a beautiful thing about it. All of this is, PVT, you can estimate from an equation of state. The rates is either measured, and the bottom hole pressures is either measured or calculated for. I mentioned this many times before, that the governing equation looks a little bit scary at first, but if you break it down and if you take a look at it, and it took me like a year to see this, and then Narayan told me, it's just like density is over equal to mass over volume, right? So we'll get there. But this is an intercept right here. This is a material balance time. So everybody that went to A&M should know what that is. This is what we like to estimate, the pore volume. This is the mass rate. So think about, we have a well with oil, gas, and water. We have the density of all of those guys. We get that from our PVT. We convert that to mass and add them together. And this guy's right here is what we call mixture density change. So what is mixture density? I don't know if I have my camera on, but I have a cup here, and I don't know what it says. Hopefully it says something positive. But this cup right here, you can fill it with 3 different phases: oil, gas, and water. They don't segregate, or they obviously segregate, so they don't mix. But you can still measure the volume of the cup and the mass of the cup, and you can kind of get this pseudo density. And that's basically the analog of what this mixture density thing is. So if you multiply mass rate on both sides of this equation, what you actually get is basically a complicated 3-phase version of this equation right here. And that equation I can still remember from university. Second thing is that it's a linear relationship, as we'll see, which is every engineer's dream, to take something super complicated and make it linear. The second part of the course today is going to be related to an tagged analysis to the multiphase FMB feature. So if I was in the multiphase FMB feature, at the top here, you'll see that there's a recovery factor analysis part of it. And that's the second thing that is required. If you have a pore volume and you would like to get your EORs and you would like them to be physically constrained, you need your recovery factors. So that's a way that you can get your recovery factors without rel perms. So your numerical model need rel perms, but this methodology is using ratios that you're forecasting empirically versus pressure instead. So your multiphase FMB provides you with this, the pore volume, how much we're seeing. And the recovery factor is needed for us to get an EOR estimate, right? That we would like to sense check our declines with, for instance, and we would like them to be physically constrained. Okay, so that's the whole reason why we have that methodology there. If you haven't used it before, there's actually 3 different parts of the software that you can do different types of recovery factor analysis. All of them are actually using the same principles. All of it is just Whitson Lake type of material balances that we'll talk about later. They will all give you the same results for the same input. We'll talk about that as well. But the way to get to the result is a little bit different. So we'll talk about that. Very good. So that's kind of the crash course, and that's where we would like to end up. So now we'll go through a little bit more theory before we're going to go through a few practical examples. We'll take breaks and stuff. That'll be good. Okay. Just if there's any questions, I have to flip back and forth to see the questions. So feel free to also speak out if you have anything. Awesome. So the only last thing we're going to go ahead and do now is to go through a little bit more detail on the theory. So I've shown you the basics once, and I'm showing you twice. So hopefully we remember it the second time. It's like when you buy a car, you have to see the car commercial 13 times or something. It's a little bit the same thing. So hopefully in the scope of the year, I've shown you some of these slides 13 times, and it's like, that resonates. Hopefully, we'll see. Or I'll force you to do it. But here we are. So multiphase FMB, in terms of the theory, a little bit more in detail, was proposed and worked on for probably 5-6 years by these 2 guys at Cimarex in this period right here. It's just a simple plotting technique, and it outputs the pore volume. So the reservoir pore volume, the oil in place, gas in place, and water in place. And it just requires PVT, production data, bottom-up pressures, and initial reservoir conditions. So obviously, like anything else, if there's uncertainty in your PVT, uncertainty in your production data, uncertainty in your bottom-up pressures, all these things, of course, they'll have an impact on the analysis. The beautiful thing is that we don't require relative permeabilities. It outputs our quantitative pore volume, does not care about geometry, assumes boundary dominated flow, and we use it to bound our RTA work. So we've gone through this already. Inverse of the slope. So small OIP, big OIP, bigger OIP. We've already gone through the equation one more time. So we've done that twice, at least, so you've seen it. But all the different pieces of the equation, we haven't actually shown you how to calculate this. And the next slide, I'm just going to warn you that that's a equation slide that we've included for reference, so that you know that this is not mumbo jumbo that we just get from anywhere, but that's something that you can go ahead and calculate pretty easily. So the density change, or this mixture density, is calculated with the formula at the top. Obviously, everybody's brains hurts when they look at these formulas, but I'll try to break it down a little bit. So this is the mixture density of oil. This is the one for gas, and this is water. This is mass rate for oil, mass rate for gas, mass rate for water. Okay, and material balance time, people know what that is. So you see from these terms, you don't have to necessarily digest everything, but it's just converting volumes to masses, and this is just calculating densities with PVT properties. So it's no real magic to it here. It's just arithmetic. But I'm not going to claim that I still know how to do this, but that's at least how they look like if you want to go in and do it yourself. you'll see typically, we'll talk about all the different phases of the plot and stuff. A vanilla envelope version of the plot would look something like this. On the y-axis, you're plotting this mixture density change over mass rate. And you see from the equation to the right that if I plot material balance time, it's actually mass material balance time, not volume, versus this value on the y-axis. I get an intercept, and the intercept is basically 1 over bm. We'll ignore that. We don't really use that for the VP calculation. And then the VP itself can be resolved from the inverse of the slope right here. So that's how the pieces are moving together. In practice, and we'll actually go through a few case studies and stuff, and hopefully that'll be fun for the group. And we'll see. We have some Eagleford stuff, we have some Permian stuff, etc. I think this is kind of the first one that I'm showing. This is I think it's a Permian example, this one. But in practice, when we're dealing with multiphase FMB, there is typically 3, especially for oil reservoirs, there will be 3 different periods. If you're more lean gas condensates or leaner fluids condensates and stuff, you probably only see two periods, but it will be analogous to this. So you'll have one period when what's flowing down in the reservoir is water and single phase oil. The compressibility of those two guys together, when they're in liquid phase, will be fairly low. And if anybody remembers these radius of investigation equations, time to end linear flow equations, etc., if your compressibility is low, then feeling that boundary takes less time. That's what we talked about before, right? If I'm in this room and I want to see all the boundaries, if the medium that I'm looking through has a lower compressibility, then I'll feel the boundary much sooner. So that's a benefit for an oil well. So typically, many times you'll see a straight line portion of the data while the well is still above its saturation pressure. And then as it goes below the saturation pressure, gas is coming into the system due to multiphase flow effects. So that's what's happening here. There's a transition period. And that is only because the gas is coming into the system, increases the total compressibility. And when that happens, seeing the boundary effects or boundaries will take longer time. That's just, that's not me, it's Mother Earth that just decided that's how it's going to be. So that's what's happening always at slope number 2. I can guarantee you that slope number 2 will never, ever be the answer because it's just an artifact of this third phase coming into the party. And then you'll have a last third stabilized slope, and that will be when you have gas in the system and you're starting to feel the boundaries. So typically that slope can be the same slope as the initial one, or it can be steeper. There's also some other special cases. Okay. But in like an environment where you're able to see this boundary dominated flow before you hit the saturation pressure and after, those slopes are exactly identical. So that's the first step. So when you have that's a first example of this is real data, by the way, no fake data. This is real data, Permian data that you see here, and a clear initial slope, and the slope later is exactly the same slope. Then we have the second example, just a practical example like this. This is also a Permian example. When you're working with real data, which slope should you pick? So you have very important, and that introduces a second thing, and that's why I love these courses, because we can just sit and talk about one feature for the whole day. So it makes all of us warm and fuzzy about that feature, so we know all the moving parts. So until now, I've just shown you, or focused at least, on the key plot. But there's probably another plot that is as important, and that's this plot to the right here, which is the bottom hole pressure versus time. And then what you'll see in the software when we run these models, there'll be a average pressure of that tank volume that you picked versus time. And that's a fantastic way of QCing whether your results make sense or not. Okay. So, and I'll try to convey that here. So you'll have one slope initially. Could it be this slope? Well, It definitely could be that slope because the average tank pressure is higher than the bottom pressure for all times in this case. If we did the same exercise with slope B and we plotted the average tank pressure versus time, we'll get the average tank pressure will be below the bottom pressure. So we know this will happen in most of the cases where you have a transition period like this. It will be below the bottom pressure, so we know it's wrong. So it's definitely not slope B. And then after some time here, we're seeing we get the stabilized slope C. We have it's a little bit steeper, so we get or shallower, sorry, and we get a higher average pressure versus time. That average pressure, since it's higher versus time, means that the pore volume is bigger. So slope C is shallower than slope A. And most likely, we've seen more of the boundaries here late time, so slope C would be a correct interpretation for this particular one. Yeah, and this is just emphasizing that again. So we pick the shallowest absorbed or largest pore volume observed to date, which is the shallowest observed slope. Sometimes, especially when you're early on and you don't have that much production data, and you have a buildup, what should you do then? So remember, all of the blue points in the plot to the left is related to drawdown because it's mass rate. So every time I'm shutting in the well, those data points are not showing on the plot to the left. Hopefully that's clear for everyone. So if I initially went in here and picked slope A, I will see that slope A violates my pick of average reservoir pressure. B actually is okay if we did not have the buildup. So, but in this case, we have the buildup, and like in any well test, when you've done well test in conventional fields, buildup information or well test information can have information that we're not able to observe just from pure boundary or from just drawdown data yet. So in this case, most likely what will happen is that later in time, we'll start to bend over even further when it comes to the plot to the left. That signal hasn't been, call it, transferred to the plot to the left yet, but in those cases, when you have a buildup, you can use that information as a way to kind of ignore the data points in the plot as long as you go for something steeper and as long as you at least estimate what the average pressure is, that it will be above the buildup, like you see to the right here. Okay, and that will be, of course, the lower estimate for this particular well right here. Okay, so most likely this well is still infinite acting on transitional, and this is a way for you to at least come up with a smaller contacted pore volume for this. If the buildup is from a frac hit, there's like external forces coming into it. You kind of have to choose whether, okay, were your exercise here to try to, yield the forecast of what the well was to begin with, or was my job here to compare pre and post, frac hit to refrac or whatever, the productivity change on the well. So if you're just using it to estimate kind of, what the EOR would be without the frac hits, you shouldn't use it. If the well is still infinite acting, what will happen is that you'll get smaller or steeper slopes in the beginning, which is smaller contacted pore volumes. And with more time, you get more and more data. And as you get more and more data, the curve bends over, and eventually you will kind of converge to what is the correct pore volume, which is what we're looking at here. In this case, it's 3.4 million STB. So just to summarize, always pick the shallowest observed slope. If the buildup data is present, then adjust the slope until it honors the buildup data. Ignore frac hits, and if it's infinite acting or transitional, it will be a lower estimate of your contacted pore volume.
Matthias, there's a question from Sarah.
Awesome. Hey, yeah, that's a great question from Sarah. So the question is related to the granularity of the data in any of these plots right here. All of these data points right here are generated using daily production data. So there's no reason. I've seen some of them, you could use hourly here in the beginning and then go over to daily. Works really well. and it should not be affected by that. But most commonly, this is daily data.
Hey, Matthias,
yeah.
kind of related question on this. Go back to that slide you're on before, I guess slide 48.
Yeah.
I know it's kind of a graphical thing, but that plot C, that slope C doesn't actually fit the data in that, even though it does honor the build-up data. Is it more important to honor that build-up data, or more important? I mean, I kind of get what you're saying there, but even if that slope doesn't match, really the slope of the data there.
Yeah, exactly. So and that's an excellent question, and it's a question we get a lot. When you have build-up data is golden. And as I mentioned, all of the stuff to the left there, they're only related to drawdown type of data. So all the blue points, we don't even see the points when we're doing a buildup. The reason why we can justify picking a slope that's doesn't match the data yet, most likely we'll do that later, is because our goal with the exercise is not to fit slopes on the data. Our goal with the flow material balance exercise is to come up with the contacted pore volume. And in this case, we know from physics, because we see that if our average pressure would be below the buildup, we're not kind of doing the best of our ability to complete the job, which is to get this pore volume. So that's why in those special cases, obviously it will not be very often maybe that you'll see it with your own data, but in those special cases, you're actually allowed to make the slope steeper than what you're observing on the data, just to make sure that you're honoring the physics here and that will still be a lower estimate. And that will only happen if the well is still infinite acting or transitional, or if there's some crazy geomechanical effects and that kind of stuff.
And I guess then too, you just have to have maybe the other course, the bottom hole pressure course, but have a good estimate. Make sure you have that good estimate of the bottom hole pressure with your data.
Yeah, exactly. So especially when it comes to buildups like this, this is actually gauge data in this example. But of course, estimating bottom hole pressures during a buildup can be pretty tricky because you don't really know the fluid distribution during that period of time. But yeah, that was something that we touched upon in that course. What we typically, our short answer there: go out to your field, calculate if you have some gauges on some of the wells, do the calculations there, pick the one that correlation that does the best job, potentially tune it. There's tuning capabilities in the software as well for that, and apply either that best correlation or the best tune correlation to all the wells where you don't have gauge data. That's kind of been the workflow on that.
Hey, Matthias, this is Matt Cannon at Devon Energy. Just to follow up on those good questions. So are you implying that maybe on this comparison that the green slope C may actually be later in time? It may not actually be fitting any data and where it is now to where it would have time to feel full boundary dominated. So in real life, this green segment may actually fit data, but it might be off the chart or not seen yet.
Exactly.
Okay.
That's really well summarized, and it's also a conservative estimate because that the average pressure just touches the buildup pressure for these wells. That is the limit, the absolute lower limit. So it's not only that it's will happen later, but it will kind of be at least what it will happen later in the life of the well. But that's really well summarized, Matt.
Gotcha. Thank you.
Awesome. Perfect. Great questions. Awesome. This well, by the way, what you see for this well that we are looking at right now is that we don't have that initial kind of single phase period and then a transitional period and stuff, and that's because we're already below the saturation pressure here. So we already have gas in the system. And for those wells, it takes more time to see full boundaries. That's just how it is. Gas is made that way. And this is also how we will look like if you apply it. I know Tracy's here and a few other companies that work primarily on dry gas assets. That for the dry gas assets, this is kind of the curve that you'll see. that just with more time, you'll see more boundaries. So there's no kind of multi-phase complexities related to that. Awesome. We'll take a 10-minute break here, and then we'll go and finish the recovery factor theory after the break. So we'll be back 9:10 here in Houston, and then we'll be back, I guess, 8:10. And what's East Coast? I guess that's 10:10, but everybody understands that we'll be back in 10 minutes. Okay, so we're gonna get started again. Hopefully that was okay breeze before the break. Hopefully people are back as well. As I mentioned, just introductionary. If some people came in late in the course, just make sure that you're logged in to the software by going to courses.whitson.com. Log in with the information that is provided in the email I sent out yesterday, or the slide deck itself. You need to be in courses.whitson.com, and you need to also use your email, and then the password that's provided also in the chat here in the Teams and in the slide deck over there. That's where we're going to do some exercises together. The course today is also, we have 4 hours allotted, but it's typically, this course typically tends to be around 3. So we'll see how much time we'll take there. The thing we covered before the break was related to the practice of the Multiphase FMB course, or the Multiphase FMB method. And now we're going to talk a little bit about this recovery factor analysis piece, which, that's just accounting. And that's why I love it, because it's like, do you trust the physics? Well, if there's a problem there's a problem with your accounting. That's the thing, that it's just material balance. That's what I love with it. So that's the second piece here. And for those who, just to emphasize that, in the software, when you do the Multiphase FMB, there's a tab here, recovery factor analysis, that we'll talk a little bit about in the course today. And I would just like to give you under the hoods what's going on there. And I know it's a feature that some companies, they use religiously on every single well, and some people don't even know that it's there. So I want to spend a little bit of time from that perspective as well. So again, we've emphasized this 3 times now, that Multiphase FMB gives us the size of the tank. That's what Multiphase FMB does. We talked about this before. To get an EUR that's physically constrained, we need to know a recovery factor. That's this guy right here. So how do you get recovery factor? By definition, the recovery, or how do you get EURs? Well, the definition of EURs is provided here. That's the definition of EUR. If you look at the equation for oil, for instance, the content of oil in place, that comes from the Multiphase FMB method. And then the recovery factor is coming from the recovery factor analysis, which is the one to the right. We'll talk about both of these. Yeah, that's the 2 pieces. It's very, very simple. So when we calculate recovery factors from a material balance, we use, I don't know if they came up with it, but at least it's mentioned in their book, and it's kind of the go-to reference on a lot of material balance stuff. So that's Whitson Lake's book on a generalized approach to primary hydrocarbon recovery. And in that book, you'll basically find these equations right here. And I know what's going on in everybody's head right now. It's basically something like this. It's a lot of stuff on the screen here. But if we simplified all these equations into, what does it actually tell us? Well, it just tells us that the recovery factor at some kind of abandonment pressure is a function of the PVT at the abandonment pressure, and how much of the relative ratios we've been able to get out at that abandonment pressure. So the cumulative OGR or GOR and the cumulative water-gas ratio as well. Okay, so that's the only thing. If we know the abandonment pressure and these things, we can calculate the recovery factor just by accounting. So it's not like, some things with like a numerical model, the interpretation is wrong, all these things. Those arguments doesn't really work here, because it's only accounting, and you will be able, as I'll show you later, if the inputs are the same, you'll get all of these the same answers in, for instance, a full physics numerical model that will be really rigorous. Okay, in the interface that we have in the software, there's 4 things going on, and we'll go ahead and do all these things together. So don't worry about it. And I'll do it in a way where I'm going to do like a synthetic well for you guys first, so you can kind of see how it feels like, and then we're going to do a synthetic well together. And then we are actually going to do some real wells. That'll be fun. Yeah. So there's 4 things going on here. The first thing is that we have a ratio forecast versus pressure. So you see there's some real data, or like this is a simulated case. So you have the green data here. And then I also have extended this curve, which you might see here, extended it to lower pressures. And I've done the same on the water-gas ratio side. This is my analysis on the FMB for this method. And then I've just forecasted the pressure. And we'll talk about, why do we have to do that in this exercise to get recovery factors? And I'll get to why. Probably the key part of this interface for you guys is because we care about oil and gas, is this how you forecast this piece right here. So a low OGR or CGR versus pressure, it gives you low recovery factor for oil. And the higher this number right here goes, obviously the higher your recovery factor for oil is. Okay, so this is probably where, and I'll show you how you QC that this number or how your forecast makes sense and all that stuff. We'll get to that in a sec. But that's probably the key plot where most people spend the most time in the beginning. Second item is why we do not need relative permeabilities as a part of this workflow right here. And the reason for that is that relative permeabilities and PVT properties, that's what gives us fluid ratios. So OGR, WGR, etc. Okay, and so, if we had rel perms in this model, then we didn't have to extend these data points right here, because the rel perms would do that for us. As long as we have a forecast of the pressure, the rel perms would take that, would do that for us. So that's why it's not needed. But here we're saying, okay, we haven't used rel perms for the multiphase FMB, so for the forecasting exercise as well, we would like to just forecast these ratios versus pressure and the pressure versus time. Pressure versus time you need anyways, no matter what you're thinking about. So we kind of skip using rel perms because we're just forecasting the ratios themselves. And if you want to convince yourself that that the ratios is just PVT properties and rel perms, you can look at this equation right here. This is producing GOR for oil. These are PVT properties, and this is a rel perm term right here, and this is the producing GOR equation right there. Awesome. So in Whitson Plus, you have 3 different ways actually to get a recovery factor. The first one would be a numerical model. The second one would be something called simple material balance. And the third one is the recovery factor analysis that we're talking about now, that's linked to the multiphase FMB. And if the inputs to all of those methods are the same, PVT is the same, abandonment pressure is the same, and essentially the cum GOR. If those are the same, then the recovery factor for oil and gas is the same. Okay? So I thought to just show you guys that real quick in the software right now. And hopefully, if you don't see my screen now, somebody needs to shout out because I'm just going to show this real quick for everyone. So I'm going to go ahead and create a synthetic well, call this a test well. I need to set some PVT properties for it. I'm just going to use a black oil to get some multi-phase effects and whatnot. And I'm gonna, just to make sure I get into full boundary dominated flow in this period of time, I'm just gonna remove any volume beyond the frac tips, and I'm also just gonna make the permeability, let me just make that like 1,000 or so. And then I'm just gonna run it on the synthetic PHP profile. Something like that. And then I can go ahead and make the historical data. I can set that historical data at equal to the inputted data. So here we have the average pressure is reached, so we know we're in full boundary here. So that is good. And we can take these recovery factors, 28, 61, it looks like. I can go into Multiphase FMB. And I could, I guess, do this with water. That should be fine. So here in Multiphase FMB, when I run it, you see that this is my oil in place. So I'm just going to go ahead and I can input that oil in place here. This number right there. And you see, we'll go through all of this later. But the slope that you see here is exactly the oil in place that I had in my model, my numerical model, full contact volume. Everything is in boundary dominated flow. My flow material balance is giving me that. And then if I took this method right here, and this is what we're going to do later. Yeah, I'm not going to do this super rigorously, but I'm going to do something like that. And I'm going to ignore that for now. I'm just going to do something like this. I'm going to make final pressure 1,000. I'm just, oops, I should have probably make that. Let me just do that. Yeah. So that's a way to get your recovery factors in the software right here. If I just make these basically the same. So you see I spit out the recovery factors here. And then I can also go ahead and do my simple material balance right here. So in this guy, I have water in the system here, so that in the simple material balance will be a little bit different. But we have 2,200. So I can do something like that. I can make that 1,000, 2,200. And I get the set of recovery factors here as well. And I probably didn't pick that to be exactly the same numbers, because this was, yeah, it was a little bit lower, so that makes sense. But the recovery factors, if I did this 100% accurately, we see basically that this is 28, the other one was 27 point something, and around 60. So they will be the same in the simple material balance, so this feature right here, in the numerical model, and in this recovery factor in the flow material balance as well, as long as my cum GOR at the end of history. So this number right here, this number right here is the same in this method, in the numerical model, etc. These recovery factors will be identical. So here you see it's 28.13 and 61. And then in the numerical model, it's 28.15, and then here we have 61 right there. So they should be identical. Okay, so there's 3 different ways, and if your if your forecast is consistent, then all of the recovery factors is consistent, and that's because the recovery factor calculation, that is nothing else than a complete accounting exercise. But the way to get the difference between the methods is in this method. We were picking the cumulative GOR at the end of history. That was predicted with PVT and rel perms. In the recovery factor analysis in the flow material balance, we used the ratios. And in the simple material balance, we just inputted whatever was the inputted number here, right? But in practice, maybe that would be, you have a DCA of oil and gas, and you would like to, you can, calculate a cumulative GOR based on that prediction, and you have an estimate of your abandonment pressure, and that would be how you can kind of get that in practice. But if you have consistent inputs, my point here is that those numbers will be identical for you there. Okay, that was the side note, but at least now you're exposed to the different means of where you can get those recovery factors, and they should be the same if the input is the same. Awesome. So unless there's any questions here, what we're going to go ahead and do is to run through a few case studies. And these case studies, the first one is a Permian case study. It's a pretty complicated one, so it'll be fun. We'll look at some Eagle Ford case studies. and then we'll do another Permian one. And after that, we're just going to do exercises, I think. So just feel free to shoot out if there's any questions as we move along. So this Permian case study right here was presented probably last year by Coterra or Cimarex. It is a Permian parent well that has a lot of things going on. It has first a initial period when it's just producing as a parent, and then we get a lot of infill wells, and then we have workover and workover. And what we're going to look at is the analysis that they did initially here before they were infilling the wells, like how they were evaluating all this data when it was just a parent. A few quick well facts. So the well was first analyzed with the multiphase FMB method. It's initially saturated volatile oil well. So that means that you go below the saturation pressure from get-go. It had downhole gauges and approximately 5 years of production. 2 of the years were only as a parent well before we got infills, and then it was 2 subsequent workovers after that. And just to note that the quality of the water production was questionable at times. And initially, they had assumed that the water saturation in the tank was 30%. Okay, so this is a real case study from a Permian company. So as I mentioned, we focused on the first 600 days. Initial water saturation is 30%. And this is how their analysis came through when they did their interpretation. What you'll see here that I haven't shown you guys yet is this. There's an option to add on this purple curve in the software. So in the software, you can add on a purple curve. It's a little bit hard to see here, but I can just zoom in. So you'll see there's a purple curve, and that purple curve will go through the origin, so around 0. And what that represents, that's basically this mixture density change at the average reservoir pressure. So that would be essentially what you'll be seeing if you had a tank and you effectively completed the whole tank and were able to drain it from the get-go, that there was no, call it infinite acting period that caused a delay to see all the boundaries and that stuff. So that would be kind of a limit. And all the blue data points should always be above this purple line, but it's off by default. But some of the, call it more multiphase FMB, I guess OGs or whatever we like to call it, they like to have that on in their plots. So that's what this purple line is. And their interpretation for this well is this straight line right here that estimates a content of pore volume of around 2.4 million STB. And when you look at if you zoom in on the data here, the data quality was questionable, but all the blue points were always above the purple points, so that looked good. You could also do the check here real quick if they looked like they ignored some of these noisy data points here. Just assume that they were bad readings, but they at least were transferring that peak right here on this one. So they saw that, okay, average reservoir pressure is above the well pressure. So that is something that passed kind of the smell test. But then they looked at the water saturation. And this comes back to one of these things that I will hopefully at the end of the day, all of you guys in the course have that as an additional tool in your tool belt, if you like. So in this case, you see the water saturation are changing from 30 all the way down to almost 7. That's what you're seeing here, almost 7. And the question is really, is that something we should expect when it comes to water saturation? And the answer to that is no. Definitely no, because water can be only produced in 2 different ways. It's either by displacement, and this is not a displacement process, or it's by expansion. And everybody knows that water expansion it's very incompressible compared to oils and gases. So in reality, and you can take a simulation model, for instance, and run it, and you can see what you would expect in terms of water saturation change versus time. But it should not be much. It should probably, it should be in single digits percents most of the time. So here they had to go back and they needed to check, what's going on with their water. So they had two paths forward from this. The first thing would be, we need to go and reevaluate the initial water saturation with the petrophysicist, because 30% is obviously wrong, at least for the whole tank. Maybe it is for the target formation that you're draining, but maybe maybe we're tapping into a lot of formations with more water. So that's one path. The second path is to perform the analysis without water, and there's a toggle in the software here that you can basically remove the water. So then you're removing a little bit of a drive from the exercise, so you'll probably typically get a conservative estimate, but at least is a way for you to bracket the numbers. So we're going to look at both of these two examples. So the first thing was that the petrophysicists, they came back and they realized that, okay, we're actually penetrating some layers with more water. And then most likely a number around 70% is a more of a representative water saturation for this well. Is it exactly 70%? Well, we don't really know. It's maybe not the perfect number, but it's at least way better than 30. Okay, so we changed the water saturation up to 70%. We redid the analysis. All the stuff was basically the same. The interpretation line was similar. All the other checks were passing out well, and the smell test here is now passed. We see what we would more typically expect, that the water saturation is changing from ish 70%, maybe down to 63 or something like that. So we see a relatively small difference when it comes to difference in water saturation. So that's the one way. And then the other way was, okay, let's do the analysis without water. So we can put that tank out, like the button that I talked about. And then we assume that the mass of the water in the tank remains constant, so there's no expansion. So we're removing a drive. So water saturation in that case can only change as a result of rock compressibility. So that will provide the most conservative estimate of the hydrocarbon in place. So if you do this for cases that have a lot of water, then obviously there will be, and especially if you're doing during single phase periods, you'll get a conservative estimate. What you'll see when we do that is that, first of all, the data cleans up a lot. It's removed. There's a lot of noise that's removed. We see that we're still above the blue points or above the purple points, so that is good. And we also see that the water saturation is essentially not changing at all. You see that here. The only changes is due to rock compressibility. Good. So we'll compare all the different cases here later. If you look at the whole history, if you bring in the whole history for this particular well, then we see that there's like an infill period, there's a couple of workover periods, etc. Except from small transients when we're including these the energy from these infill wells, the slopes basically come back on a similar slope. And that brings up the question that I kind of talked about earlier. If you have these small parts of the data, if you have a bash or a frac hit, or if your system gets energized by an external source or not, depends a little bit on the objective of what you're trying to address. So is it okay to then ignore this external energy, or is it not? And that if you're trying to evaluate a refrac, you should probably go and include it. But for just primary depletion, like here, they chose to ignore this refrac period right here because that's external pressure forces, or I guess forces in general that adds on to the productivity. And here it was actually a special case because the refrac had a positive impact on the parent and not a negative. One last thing to check is just if your slope.
Wait, Matthias, just to clarify, they did a refrac, or that pressure was only from the offset well's interaction with this well?
Yeah, exactly. So this is not a refrac. So this is just from infill wells. So this is actually a positive impact on the parent from having infill wells drilled close by.
Okay, great, thanks.
Another thing I'd like you to have in the tool belt, and now we're getting into like, okay, now you're becoming an expert, really an expert. And that's when it comes to if the slope of your interpretation and the purple line right here, if they are not parallel, here you see that they're not perfect parallel. You can use that as an indication to sense check your compressibilities. So if your average plot is too steep, it means that your rock compressibility is too large. And then when your average plot is too shallow, the rock compressibility is too small. And in this case, they reduced their rock compressibility, and they now to something that made more sense for them, and they basically got these parallel lines. Anyways, so that was another thing you can keep in your tool belt. So it's kind of three things. Always sense check your average pressure versus your bottom hole pressure. Sense check your water saturations, because water can be important. And also you can use that line, but then you're becoming an expert if you want to sense check your rock compressibilities. So if we summarize these cases up, we see that with 30% water, our oil in place numbers, I'm going to focus on the ones in the middle. They're around 2.4 MSDB. If we accounted for 70% water saturation, it was changed to around 2.3. And if we had no water, it was 2.1. No water with 2.1, that's kind of what you would expect. That would always be the lower estimate, because you then removed a not a super effective drive, but it is a little bit of a drive. If there's any questions, I'm just going to double check that quick. Yeah. Awesome. Second thing we're going to go through is an example that Trevor Stokes and Stephen Young at Devon did, and they wrote a paper for it for UTEC last year, and that paper is using this methodology to evaluating refracs. So the short story, this is actually from their presentation at UTEC, but I'm gonna just run through that presentation, kind of a very abbreviated version of it than what they did. So first of all, what they did to be comfortable with that the methodology would capture the uplift from a refrac, they went in and ran some synthetic examples. So they took a well that was producing for a period of time, and then they doubled the number of fractures in the simulation model. And then they ran that simulated grid into the software. So they created this simulation case right here in Whitson Plus, and they just, after a period of time, they just increased the pore volume. And then when they did that methodology, before the refrac, it captured the right pore volume, that was 3.5 million SDB. And then after that, they contacted 7 million SDB. So that was the sense check they did first, just to make sure that the numbers added up, so they could feel comfortable that the delta change in slope essentially was a delta change in whatever they're able to contact. So in the Eagle Ford, they went ahead and did this for a wide range of different wells. They, of course, repeated the fact that we have these 3 different periods in the plot. We have initial period when you're undersaturated. If you look at here, and you have this transition period and the third period. So that's what we talked about before, that you have the single phase period, you have a transition period, and then you have a third stabilized period, okay? And this will always, like, you have 3 different outcomes, and this will always lead to 3 potential scenarios. Only 3 potential scenarios. The first one, which is really common, is that your early slope is steeper than your late slope. That means that your early contacted pore volume is lower than the late contacted pore volume. That makes sense. you're still infinite acting early time, and then take some time before you get into boundary dominated flow, then that's how it would look like. The other extreme would be, or the other option is that the early slope and the late slope, they're identical. So you're basically contacted all the pore volume early, and you've contacted it late, so those slopes will be the same. And then the third option is basically if the early contacted pore volume, if that is larger than the late contacted pore volume, which we see a lot of in the Eagle Ford, and not necessarily that much in other basins, but if you observe that, we see that in many of the Eagle Ford plays, it's typically due to a loss of surface area with time, or that there's really strong geomechanical effects. And I'll talk about that in a special thing later. But when you introduce geomechanical effects as well, seeing full boundary effects will just take way more time. Way more time. Okay, so just keep that in mind. So for a field example, this is a field example for one of their wells, real data. Early time, they're observing 2 million SDB. Late time, they observe 600 MSDB for this well. And this is a well with probably, tons and tons of production data. And, the actual contacted pore volume effectively, since it's actually changing over time for this well, is somewhere in between these two. Okay, so if you wanted to, it makes like a recovery factor calculation a little bit tricky. But that's just how it is, and you can use that almost as a diagnostic tool to, oh, these wells have that characteristic. Well, that must mean that this and this and that thing is happening. So if you look at a successful refrac case, what you're then left with is a way to go in and take a successful refrac, and you analyze the early time slope change, pre and post refrac. And you do the same with the late time slope change, which you see in this example, and you compare the uplift, which in this case is almost 2x in both cases. And that makes sense. Like, you would always like that your EUR uplift and your MFMB uplifts, they should be at linear scale. And why is that? Should that be a linear scale? That was because what we talked about earlier, that your recovery factors multiplied with the contacted pore volume is your EUR. So this is a nice way to QC that. Then we have, of course, an unsuccessful refrac. Can't just show the good ones, right? We have to show a mix. So this is an example of where the refrac was not as successful, and we had the early time slopes basically show the same or very small uplift, and the late time slopes showed something very similar, and you could actually kind of see it also in just doing the decline curve analysis. That's how that would look like for not a successful refrac. So Trevor and Stephen, they analyzed both 29 actually refracs. This is all in this paper that they wrote, and they summarized all the early slope deltas pre and post refrac, and they did it with the late time slopes as well. Both of this showing here. Actually, the average of both of them were 80% uplift when it comes to the increase in contacted pore volume, and they also used that to create this correlation between the difference in EUR uplift and what they saw in the delta change. So when you have some of the wells have had a lot of production data, so you can have a pretty good confidence on your EURs, and then you compare that with the delta in uplift there. And here it's important to say that this early time slope was picked after 15 days. So their summary was basically that they could use this early time diagnostic of a refrac, and after 15 days pretty comfortably say whether or not there is a long-term impact of that refrac. The method also accounts for multiphase flow and superposition, so that's also a big thing, especially when these refracs are done below the saturation pressure. And it can also differentiate between, okay, are we actually adding reserves here or just accelerating production? So that's a quick case study on using it for refracs, but the same concept, and hopefully at the end of the day you'll know all all the nuts and bolts of this, seeing we're doing pretty well on time. I'm just going to. Good. So the last case study before we're going to do the exercises together is related to using this methodology on a set of wells in the Permian, not looking at this as not doing this exercise on one well, but can we actually do it on all the wells on a pad and say this is the content to pore volume of all these wells at the same time. So counting for like well to well interference and all these things. So a synthetic example is always where we start. So this was a paper that Leslie and Barry were putting together for UTEC this summer. We started with a synthetic example, similar to what we did with the refracs, where we had a parent that produced for a period of time, I think 2 years. And then we had 2 infills that came online. So to just highlight that, we had the rate and bottom pressures for the parent. And then after a period of time, we got the infill wells in, and they were put on production as well. And they were put on production after around 2 years of production, or maybe actually exactly at 2 years. And at the 2-year mark, if we looked at the density distribution in the reservoir, it's like a way to look at saturation, basically. You would see that in this particular reservoir model, there was a very, very effective drainage inside of the frac tips, but since the permeability many places in the Delaware and stuff is like in the ranges of, it could be like 1,000 nanodarcy or 2,000, etc. That was at least what was put into the model. You see that there's considerable contribution beyond the frac tips. So when we're putting in these infills here, the infill well should not have a contented pore volume that is as big as if this parent wouldn't be there in the first place. So when we want to use multiphase FMB on a wide range of wells like this, we kind of have 2 alternatives. The one alternative is to go ahead and just do the multiphase FMB method on each of the individual wells, and then add them up together. And then we'll end up with a total pore volume like this. So that's fair enough, that's easy. And if you do that in this case, you'll end up with this example right here. So you get the parent well, since the parent well is draining its basically stimulated rock volume and a little bit beyond the frac tips, that pore volume will be larger than, or the largest of the 3. The closest infill will basically be tapping into a pore volume that is the closest to the parent. So that's tapping into a lot of already existing drainage. So that pore volume will be a little bit less than what the whole stimulated rock volume for the infill one. That's why that's the lowest one. Then infill 2 is basically not have really not been drained that area at all. So the content pore volume is probably close to the stimulated rock volume. If we add all of these numbers together, we get to a total pore volume that's just 3% off what it was actually put into the model. So for a synthetic well, at least, it looks pretty good just doing it like this, even though there is well-to-well interference and stuff. The second thing would be to create a pseudo well. That's a second way of doing it, where you take all the wells and all the rates from all the different wells, you summarize them together, and then you take their bottom pressures and you create a pseudoized bottom pressure for the whole block, if you like, that is just a mass-weighted average of the individual bottom pressures. And you just put that into like one well in Whitson Plus. That was essentially what was being done. So we do that exercise with the method and call it the pseudo well method. We see that we have 2 slopes, one before we put in the children, I guess, and then one after. And that pore volume was around 12.1. So that's a little bit more off, but 5% off. So still pretty close to the whole content report. So bringing this over to a Permian example, we did this, when you have a real well and a real pad where you would like to do this, there's no option to kind of, you don't really know what the real answer is. So maybe you can just go ahead and do both. And you get one answer that is with the pseudo-well approach, and you can get one answer with just adding all the individual wells. So this is a real pad in the Permian, had 8 wells on it. And the alternative one was to then go ahead and analyze all of these wells individually. And here is the analysis of all of them individually. So you've seen how this is most likely a saturated reservoir, by the way. So you don't see this initial period that's straight and then it goes to a transition period. It's just straight into this transition period right there. So you can take all these different analyses and these interpretations, and you can go ahead and say, okay, these are my different interpretations for these wells, and you can go ahead and add them up together. Alternative 2 would be to create the pseudo well of all of them. And you see the highlighted portion of the data. That's when it was only one of the wells there, and then the other one is basically when there is. I get my dog is barking a lot. Just give me a sec. So that's the second option on that.
What kind of dog is that?
One more time. What
kind
kind
of dog? Yeah.
It's a mutt. So I need to double check exactly what it is, but anyways, sorry about that. Very good. So that's the second option right there. And then you can take the wells and you can basically add them up individually, or you can create a pseudo well all together like this. And if you compare the two results, fairly similar. The individual wells gives a little bit lower estimate in this case, and the pseudo well gives a little bit higher, but same order of magnitude, which I think is what most people here is interested in. Awesome. So just a couple of frequently asked questions that I'd like to just touch upon real fast. The first one is related to what about a dry gas well? The thing that a lot of people don't realize is that even though you have a dry gas well in the software, you can actually run the Multiphase FMB on the dry gas well. So I'll show an example on that. There's also a dry gas option, but you can still use the method for dry gases. Yeah, but we also have the Auger well dry gas FMB in the software. The difference is the concepts are all the same. The difference is that it's an iterative method if you use the Auger well. And the Multiphase FMB is not. But I'll just demo this real quick so you guys see it. So I'm just going to create a gas well. So hopefully everybody can see the screen. I'm just going to call this gas well. When you add a gas well in the software, you just pick the dry wet gas. I'm just going to make this a dry gas. So I'll make this 0.6 specific gravity. Then I'm going to run a numerical model. Just want to make sure that this goes into full boundary as well, so we can apply some of these methods. Maybe I'll just add this will have water in it. Should I just remove the water maybe? Just so we can have some fun with it. And then my perm is 1,000. Okay. So if I take that, I just run it and I upload that as rates. So for those that don't see it, I can go up to the right here and I can set historical rates equal to simulated data. And what that does is that it then databases these rates as inputted production data in the plot here. So we obviously see this goes into full boundary, yada, yada. So in the flow material balance then, we see that the FMB type by default is predicted to be gas. Okay, so that's there already. And we had an OGIPS that was around 14 BCF, and I can go ahead and input that into the software for this particular well, and I can reset my slope, and we see that's a perfect fit on the data with when you compare it to the numerical model with the gas FMB. What you'll see is when you do it, you might have to move this a couple of times because every time you move it a little bit, the calculation is redone. But that's just because the Auger well material balance of this guy is iterative. Then I can go in here and run the same method just for multiphase. and you'll see the same thing. If I just take the pour volume here, and this is, you know, when I run it multiphase like that, that it's giving me an exact spot on thing on the line here. So it's the same. So it gives you the same pour volume as long as these in boundary dominated flow, it gives you the same pour volume. So that's just something I wanted to emphasize, that you can use both methods. The constants are the same. The slope up and to the right, the inverse of that is your pour volume. And you have to be in boundary dominated flow in both of them. And if anybody on this planet is telling you that you don't have to be in a boundary dominated flow to use a flow material balance, send them to me, because I'm going to have a chat with them. And I see the Whitson plus icon here was yeah, anyways. Good. Then another frequently asked question is, what about pressure dependent permeability? And then I'd just like to show you guys that with a quick example here. So let's take this well where I had the gas, and the only thing I'm going to change is that I'm going to make the matrix pressure dependent permeability 6, which is actually a number that people are using some places. We've seen measurements above 10 actually in many places. So if we take this data and we set it to you know, the same thing, we see that the curve, the whole shift of the curve changes a lot, and we also see that the average pressure is a little bit above at the end of the history here. So what will happen is, when it comes to both the gas FMB or the multiphase FMB, doesn't really matter. But if we rerun that, the methodology changes, or the curve changes a little bit. So you see it will take longer time until you actually are on the right slope. But eventually it gets there. But it takes longer time than in the other case. So when you introduce a pressure dependent permeability, which a lot of you guys love to do, and I do it a lot myself, not gonna lie, then just remember, if that's your mental model of a rock, if that's your mental model of the Eagle Ford, of the Marcellus, of the Utica, wherever, then you should expect to see boundaries later. For everything else being the same, the boundaries should then appear later, and you'll be in this what looks like a transitional flow regime much later. If you looked at some of these like diagnostic plots and stuff, like your deltas would look not, you know, a perfect line of 0 for that period of time, but you might be in like, you know, 0. You know, whatever this delta is, 0.17. This is a little bit of an off bit. So just keep that in mind if you do that. If that's your mental model, it will take time to see your pressure dependent permeability. It can even take many, many years. So it's a combination of your actual perm, your completion, and that pressure dependent permeability now. So that will be my second hour here. And then the last hour, the only thing we're going to go ahead and do is to do exercises. We'll be back here at 10:12, and then we'll just go ahead and take it from there. And just feel free to shoot out if there's any questions or anything. Awesome. So we'll go ahead and get started with the exercise piece, which will be the next part. And the only thing we're going to go ahead and do there is to spend some time. First, get to know the interface. We're going to run some data and stuff. That's going to be good. Just before we do that, I see from looking at everybody here that yeah, there's a lot of folks that I know use the software a lot. So I'm going to skip some of the software basics, but I'm going to repeat two things when we get there. I'll spend a little bit of time on that. That's related to the Zoom and a couple of things. But I would like everybody to go into the software, make sure that you're inside of your project. If you have not created a project yet, you need to let me know now in the chat. If you came in a little bit after the first ones when we created the project. If you have created a project, you should have 3 wells in there. And if you don't have 3 wells in there, you also need to let me know so I can help you with that. Give everybody a couple minutes there. Okay, perfect. The thing we're going to do now, the only first thing we're going to do is to take a well, and we're going to use it not to analyze the well per se. Maybe we'll do that as well. But the more importantly, what we're going to go ahead and do is to use it for getting familiar with the FMB interface. So we're going to just click this first well in your project. You're going to go into PVT, and you're going to run the PVT. Okay, so I'm going to show that again. You're going to go to the well that's labeled number 4. You're going to click it, go to PVT, and you're going to just open this fluid card here and run PVT. So that's the one input you need to be able to run this. Okay, so we have PVT and production data, and here we're just going to use the gauge pressures that's been uploaded by the software. So that's in the bottom of pressure. That's what's already being used. We're not going to calculate any bottom of pressure here. That's not the objective of the course. And we're going to take the PVT. So hopefully everybody's come here, and we're going to go straight to the flow material balance. And we're just going to calculate by clicking the run button up here. Okay, so I'm going to repeat those steps just because I want everybody to join me here. So I'm going to repeat those steps. The only thing you're going to do is to click well. I'm going to pick the first one. I'm going to pick PVT. Open up the PVT card. Click save. And go to flow material balance and click run. So 2 clicks. And it should look something like this. Okay. At the top here, you see that's where the toggle is. And I'm going to loop through every single part of this, because that's what the course is about. We're going to spend more time than what we typically do. Here at the top is where we flip to potentially gas FMB. Gas FMB, like Multiphase FMB, you can always use. Gas FMB, you should only use if you are dealing with a dry gas or potentially a wet gas. And how do you know what fluid system it is? Well, in PVT on the black oil table, it will always say reservoir fluid classification up here to the right. Awesome. So that's how you change it. When you run it the first time, that's just to get these blue points on the screen that we can go ahead and interpret. These blue points, they will never change. The only thing that might change after you move this line up and down is how this average curve versus time is, but we'll get back to that. So we zoom up to the upper left. These numbers right here, they're connected to the line. So this line right here, if I change the slope of this line, you'll see these numbers will change. Also, if I make this line another number, you'll see that the slope is changing as well. Okay, so these numbers right here are connected to the line. So a steeper line, that's a low contacted pore volume, and this is a higher contacted pore volume. Easy enough. All of these are just connected together with PVT properties and the pore volume itself. And they're linked to the slope here from the equation that we looked at earlier. Remember, like there was a straight line and it was a 1 over pore volume. So that pore volume is this guy right here. And then from a pore volume to a oil in place, gas in place, and water in place, it's just water saturation and PVT properties. That's it. Here, these are the initial conditions. That's typically stuff you have introduced in your PVT part in step number 1. We're going to assume that that's correct in this case. Water saturation is an input, and rock compressibility is an input to this exercise. There's a toggle here to include or not include water. So in the cases, I know for the Devons and other companies that have these Permian assets with a ton of water production, if you have, and also in other basins as well, where you have a really big kind of water gas ratio, whatever, then and that might be uncertain sometimes, you could do the analysis with removing water and then including it, and you'll basically bracket your answer. That's very popular for people. And the last piece here is just the slope. And I think I can just change the slope like this. Okay, yeah. So these are also related to the graph here. Awesome. So that was the stuff on the left.
Matthias,
yeah.
Sorry if I missed this in your earlier comments, but that initial water saturation, the one you initialize flowing material balance on, is that total or is that movable? Like, since we're not including rel perm considerations, how do we think about that with this type of analysis?
Yeah, that's an excellent question. That's an excellent question. So did everybody get the question? It's like, since rel perms is not an input into this model, like explicitly, that's important for me to emphasize. It's not explicitly an input to the model, but these ratios and whatnot, they're kind of implicit. So this initial water saturation right here, that will be the total water, and you'll see that is linked through all the features, also the features that requires a rel perm as an input. So the movable water, that will be the delta between that water saturation there that we input and this Conit water saturation guy right here. So to Matt's question there, it's the total water saturation, and it doesn't have to be necessarily the movable part. If there is a difference between the, if there's a huge immobile part, and if you put that into the model, the multiphase FMB would actually capture that, as long as you use the correct total water saturation going into the model. But I realize in practice it can be hard to know what that actually is, and maybe with a lot of high degree of certainty. So that's why we love these plots to the right here. Great question. The next things we're going to go ahead and do is to take a look at this plot here. There's a lot of things going on, but we're not going to even think about these points just yet. We're going to focus on how we can do different things in the software. One thing that you'll see that can happen sometimes is that this slope, and this is for everywhere there's a slope in the software, multiphase FMB, analytical RTA, fractional RTA, you name it. There's a slope there, and that slope goes outside of your screen like this. There's a button, reset slope. Okay, just like that, reset slope. So I would go ahead and just make sure that if you ever lose it, let's say I zoom into a part that doesn't have the slope in it, just click reset slope and you're good to go. So that's the first thing. I'm going to start at the top here and move my way over. At the top here, you also see that there's two different options here. This is the mixture density change at the bottom of pressure, and then for if we have an estimate of the average pressure versus time, which you have implicitly when you run this, then you can toggle on this guy right there. That's the hard check that I showed you guys earlier. Here, if you toggle this on, I know that my last run of a contacted pore volume is not correct, because this purple line is basically interfering with the blue lines. That's also what you're seeing here in the plot up to the right, which I'll get to later. So we know that this is not the right fit. There is a lasso fit option. So what you could do is you could zoom in to the lower left of the plot. Now I lost my slope, so I can just reset it like this. I can take my lasso fit, and I can take this data right here, for instance, and then it will fit that data. The one, another thing is, in this case, for this well, we get into the interpretation of the well and stuff later. I just want to show you all this. There's also a lasso highlight option. So if I click this and highlight this data, then that data here will also be highlighted in real time over here. When is this data? The reason why that can be helpful is, this is material balance time. It's even mass material balance time. It's so abstract you don't want to even think about it. So you want to have a way for you to translate that into real time. So that's the highlight option. And the highlight option has 3 different things: lasso highlight, lasso remove highlight, or remove all the filters. So if I remove all of them, all of this stuff disappears. Another thing which we got a feedback for, and I think maybe Donovan was one of the guys that made a feedback. A lot of people gave this feedback. It's what is very annoying with these plots when you want to move the slope, the end of the slope, is that there's just very little difference between these different symbols. So now you see my symbol is a hand, and now it's a zoom. So if I start to now try to drag it now, I'll be like, now I was actually doing the lasso filtering, but if I was just doing the regular zoom thing, then I would be, doing something like this. So that could be really annoying. So in that case, we have this lock zoom capability. So if I've zoomed in to this portion of the plot, and I don't want the axis to change anymore, I'm happy with this, whatever this is. I don't want it to change. Maybe I'd like to only focus on the early time portion of the data, for instance. So that's what I would like to do. Then I can click lock zoom, and then I can't, even if I'm outside of there, I can't zoom on the plot. I can't move the axis or anything like I'm typically able to do. So that's what lock zoom is. So the workflow would typically that you would zoom into where you would like to do the slope moving, and then you would lock the zoom for that purpose. And here is just export to image, export to Excel. Here you can change by clicking the zoom axis. This is kind of the old school way of doing it, as I like to call it. So you can click here, and you can say, okay, I would like to pick my minimum at the X and the maximum at, 10,000, for instance. I would like to change this to, 2, and click save, and then it changes like this. Okay, so that's a way for you to do it the old school way. This is the reset zoom button, and then this is the expand. So you'll find these in a lot of the other plots as well, and that just makes that it takes up the whole screen real estate. And the expand will always be up to the right, and collapse will be the opposite button. So you just click it again. Awesome. So I think that's clear. That's great. So we have the basics on that front. Just for the 2 things I wanted to just mention: Control R, refresh. If something isn't working, make sure to refresh. All the run buttons will always be up to the left. They will be in primary Whitson blue. And the last thing that I'll mention is related to the zooming of the plots. If you don't want to do it this old school way, up here, you can drag the ends of the axes. You can't not be in the middle, all the way to the end. That's how you zoom it. Also here, you have to be in the end. Here you can also go in and say, okay, I would like to go in here, click, and I would like to actually type in a number myself. Same here. I would like to make this 500. So if you go all the way to the end of the axis, you can click it one time, the number appears, and here you can type in whatever number you want, and you can click enter, and then this thing zooms. Just wanted to mention that. And of course, if you just click anywhere on the plot, you zoom into that. So hopefully I've touched upon all the most important things. Now over to this. That's kind of the practicalities. And if you don't know these things, doing this can be really frustrating. Trust me. But if you know it, it's not that bad. It's actually pretty okay. For this well, we are dealing with kind of these 3 different periods. Late time, we're also dealing with a lot of bad bottom hole pressure readings. So over here, it's really tough to even get any interpretation. The most shallow observed slope in the data set I can just visually see is down here. What I would probably do in this case would be to go in and pick a slope. Looks like it kind of curves over. Then we get into the multiphase region. How do I know that? Well, you can add the lasso highlight. And I see that this is just before I get into this period over here. It's like around 3,000. And I think if I saw my PVT saturation pressure real quick here, that was around 3,000. So that's how I feel good about it. And also when you've seen it 1,000 times, honestly, you know that differentiation, that's you're hitting the saturation pressure. That's what's going on. So this will be my, something along these lines. And then you can, we can, is it more like this? Is it more like this? Etc. But something along these lines would be my interpretations for this well right here before we get these multiphase effects. Curves nicely up here, and that would give me somewhere around 800 MSDB. And I'm a round guy. I'm a round number guy. 800. That would be my number. When I'm happy with my pick of a slope, I just need to rerun one more time. And the reason why I rerun one more time, that is because that will update this average pressure calculation versus time. Nothing else. It's only for me to do this QC over here. So I want to make sure that all these black points here are above the bottom hole pressure, everywhere where at least I think the bottom hole pressure is good calculated. These, I don't know, these points over here, I don't really care about. So that's one of the first smell tests. The second smell test on this one, this is the SBE data set, so I'm just using the values that they gave me, and I'm just pretending that they have a really stubborn geologist, so I'm not allowed to change the water saturation. But if you wanted to be honest with this, like the water saturation here is changing from like 30 down to 0, even at close to the wellbore. That's never going to happen. So most likely, the water saturation here is wrong as an input. Just wanted to mention that. So that's one of the smell tests that you can go in and check. And this is a nice smell test, by the way, to just do. Even if you're infinite acting, like just as like this is a tool thing that you have in your toolkit, and you can, that's a nice way to just check, if my water saturations make sense in the first place. But of course, oil saturations, they will change a lot because gas is coming out of solution and that kind of stuff. So I think everybody follows that. Last thing, if you wanted to, you could include this guy right here, just to double check that all the purple points are basically below the blue points here. If that's the case, then you also know that the black line is always above the gray line. Okay, like this. So this is all makes sense. If I picked something that was inconsistent, you guys don't have to do that. 800, hopefully you get something around that, but I'm going to pick something that's inconsistent, something like that, just to show you how that looks like. So how that looks like is that, first of all, up here, my average pressure is below the gray pressure. Of course, all the blue points is the same, but my interpretation of the tank size is different. So my back calculated average pressure will then change. And you also see if I plot this number, you see that the average thing here is way off. It is above the blue point, so we know that that's not right. When you look at this, you see that already, but that's just a number. Good. Yeah. So I had 800. So that's going to be my final answer here, and then we're going to go over to recovery factor analysis, which is the next feature right here. That's a feature that requires a little bit of training, and that's a feature that some people love and some people don't love. So that's just the way it is. That's the way the cookie crumbles, as Jim Carrey says. So just go to the second tab here, recovery factor, flow material balance, and recovery factor. And then you see there's some steps missing down to the left here. We've already forecasted our bottom hole pressure, and that's the final pressure there is 700. If you want to, we can change that down to 500 if we want to. So let's just go ahead and do that. So these forecast assumptions is what is happening from the end of the bottom pressures here and out. And you can change the starting pressure, etc. But for a flow material balance exercise, it doesn't matter, because the only thing we care about is the final abandonment pressure. And that's essentially what the recoveries will yield and give you. Good. So that's number one. The second thing that we did, and we've already done it, is the flow material balance. That was step one. So we've done that already. So we know the tank size. We forecasted the average bottom pressure versus time. And now instead of using rel perms, we're going to forecast the ratios. And the most important part of where we forecast the ratios is in the period where we forecasted our pressures. So we can do a lot of fancy dancy stuff up here, but it doesn't matter because we're never using those properties. The same here. Use the same thing here. But just to, and this data is really scattery as well, so I think it's a good example of how you also need to have some tools to QC it real fast. But we would like to add this trend versus time on a data. And to do that, we can click Add Points here at the top. And actually before that, I'm going to do the same thing just so everybody's on the same page. So the estimates here to the right, that's all the contacted volumes that we resolved from step one. This is what we like to calculate. So after we click Run and do all the stuff here, that's what we're gonna do. The reservoir abandonment pressure, that's going to be a QC that's going to be printed out after we've done the run. So I'll get to that. The BHP forecast assumptions, that's just related to this plot right here. The interpretations, that is just related to the multiphase FMB slope. And the checklist, have I done everything before I need to click Run? And here we're missing OGR versus bottom pressure and VGR versus bottom pressure. These two slopes. Some questions is like, why do you use OGR and not GOR? The reason for that is if you want to use this for like a dry gas, there's no OGR. So that's the only reason. In these plots, all of the plots are expandable, like this. They have all the same features as all the other plots, zoom lock, etc. And they have these 2 points that you see in some of the other features, like the smoothing of the bottom of pressure, you name it. So what is relevant for this guy is the plus icon here. You're going to click it, and you're going to create the trend going from high pressure to low pressure. You can do something like this. And then most important is not what you're doing here, but it's from 1,000 going down to wherever. And I'm going to show you how to QC this after, but just do your best job. When you've done this for a lot of wells, you'll be able to do this just eyeballing it. Maybe you would like to use some analogs or some simulation models if you like to do that to come up with a good trend forecast versus in the future. But you need to do this for the OGR. And there's a reason why it dips up and down. We'll talk about that in the PPT course. And then also here on water, you can just do something like this. Make sure that it curves such that it doesn't go through zero, this stuff. That it's at least some water at some value, that there's a positive intercept here. Same here. Okay, when you're done with that, you go ahead and click Run. And what the software then goes in and spits out for you now is a recovery factor in the contacted pore volume, right? So in the petrophysical, we will probably divide this by 5 or whatever, for gas, oil, and water. Okay, so around 186 for this guy. And you don't have to do this, but if I did an autofit on this, looks like that's around 200. Okay, so it's not too bad. It's pretty aligned. 180, 186. Good. But I want to QC whether my forecast of OGR versus GOR is okay. And this is the most important part of if you want to use this feature for this. And it's toggling this GOR versus oil. And that prints the historical GORs, and it prints the forecasted GORs, sorry, to the end of history. And again, if you wanted your numerical model, your simulation model to give you the same recovery factors, just make sure that you have a GOR at the end of history It gives you 2,400 in this case, and you get exactly the spot on the same recovery factors, which in this case is in the contact pore volume 20, almost 23, etc. What you would like to avoid here is that you have a purple line and then suddenly a very different trend, either shooting up or flattening out like crazy. You would like that to be fairly continuous. I'm a little unsure if I'm super happy with this, or if I would like to maybe even bring it down a little bit more. So if I wanted to do that, then I would have to increase these data points right here, just a slight bit. That will increase the recovery factor, and at least that it will look a little bit more continuous when I would go up and do that. And that brings me back to this plot that I was showing you guys earlier, which is this plot right, this guy right here. So higher recovery factor is up, and that also means that your QMGR goes up. So now, yeah, it's flattened a little bit, moved a little bit down. Maybe I feel better about this. Also now my oil EOR is really in line with my DCA. Not that I necessarily intended to do that, but it's that also, I don't know if that makes me feel good or not, but, but that's at least a way to check it. And of course, when you've done this on a ton of wells, it's easy peasy, and maybe you generate some ways to do this yourself. But this is the way you QC whether that makes sense or not. And here you get your EORs out and your recovery factors, and this is just a QC that you put in a final pressure of 500, and that you're basically meeting that final pressure of 500 before it's gone like 50 years or whatever. Awesome. Any questions here? Or I think we're good on that. We're gonna do. I was thinking we could do. We'll just go ahead and do the other two wells as well, real quick, and I think that'll be it for today, actually. So the Crow well is well number 2. We'll just go ahead and run the PVT. Says in wells, and then you pick PVT here. You run it, go straight to flow material analysis, and click run. Okay, so hopefully everybody's here. The interesting thing with this data set is that there is a buildup here. We're going to pretend that that's kind of a correct buildup. So before we hit the saturation pressure, we're going to go in here and pick a slope. That gives me around 750. And here we see that, okay, if we think that these buildups here is actually a true buildup, then we are allowed to pick a slightly shallower slope here in the data. Maybe up to 2, I don't know. Let's see what it requires. Maybe 2 million. Yeah, that's probably better. Maybe even a little bit more. Okay, so everybody sees that you could go in and allow for you to have slightly shallower slopes that you honor this buildup right here. This is a very important QC. Awesome. Then in the second step, we just go in to the recovery factor analysis, which is this guy right here. And we're going to go in and we're going to just add these data points again. So hopefully everybody has been able to do this okay. Changing the slopes is just by grabbing the ends of the axes like this. If you want to just move the whole thing, you need to be in the middle. Then here you do the same thing that you did earlier. Forecast the CGRs versus pressure. Something like that maybe. And you do the same thing here. Make sure that it doesn't go through 0. And then 700 is probably fine. And then you click run. And there's tons of companies that this is what they, it's almost like their go-to method of getting physically sound EORs. And here I have a forecast It looks okay in the future. My EOR is around 443. I don't even know what my DCA said for this guy, but just check it real quick. 532. Maybe I could make some adjustments to my DCA to make sure that I get something similar to this if I believe that this is the answer. Or maybe, you know, if it was a higher number right here, the recovery factors would go up and my EORs would also go up. Okay, any questions here? Is it easy enough? I'll interpret that to be easy enough. And then the last well that we're going to go ahead and do is the pheasant well, number 37 in your well overview. Number 37 in the PVT. I'm going to change the PVT to this dry and wet gas well and make it 0.6. So I'm going to show that again in PVT. What you're going to do is that you change the method from GOR to dry and wet gas. And then you just make it a 0.6 specific gravity fluid. And there's no phase envelope here. That's fine. But yeah, it looks like this. And that's because it's a dry gas well. So you see that this is the dry gas table it creates. And we're going to do the flow material balance again. But if we go to flow material balance now, you see that now it is a different method, and it's by default going to the dry gas material balance. The only thing you do then to grab this slope to your data, you release it. Software will calculate it one time. Then maybe it requires a couple of times just to converge. And then once it's converged, you pick the slope. This gives me 2.2 BCF for this well. The same checks apply. The same things with the reset slope and the lock of the zoom applies. And I can go in, change the method, and run it with the multiphase FMB as well and see, okay, with a different set of eyes, a little bit different method. Here I'm getting around 23.6 looks like for this one. So 23.6 versus, I don't know what I had here. Yeah, 22.6. Yeah.
So I guess in the software and the database, it saves as kind of two different analyses, right? Whether you're doing it multi-phase or as gas flow material balance, one of these is not going to change the outputs of the other.
Exactly. So when I go in here, that's a great question. And I just, let's say I want to export the well information here, for instance. So that's all the calculated stuff. So if I just open that file here, you'll see that there's different columns for the multiphase FMB and the dry gas FMB. So that is referring to the different, yeah. So here you see the multiphase FMB numbers, that table, and then the same goes here for this guy. So this was 23 point something, and the other one was, yeah, 23.6. So that's two different tables. So you can do them in individually if you like to, and also get them automatically from the API and stuff like that. A couple of things we're working on flow material balance, just as like a little FYI here at the end. I think in the next few months here, hopefully, it will be like an auto-fit functionality to the methodology. One reason why that is much harder, like if you go to analytical RTA, for instance, we have these auto-fit functions, and they work pretty well because the data, even if it's noisy, there's like things you can look for. How to interpret a flow material balance plot needs to be a little bit smarter. It needs to know something about, okay, the saturation pressure, are the data points before the saturation have a little bit more logic into it. So that's what we're trying to think about, if we can come up with a more educated way of doing kind of an auto fit for this option. And the same goes here, if you can come up with some ways of doing like an auto, kind of an auto fit for that as well. Let's call it an auto fit, where you can get at least a starting point for some of these curves right here that is not far off. So that's hopefully going to help to give a good starting point, and maybe we can add some more points on top of it. Good stuff. So that was a lot of material balance. I'm going to probably end it here if there's no other questions. We'll of course distribute the recording and everything and the slides. It is a little bit of a special topic. The methods, just to summarize, the most important thing for you to remember is that it's different from RTA in the fact that it's only trying to find the size of the tank. It requires less input than an RTA exercise because it just needs PVT, production data on bottom pressures. It assumes boundary dominated flow because we are trying to actually get the size of the tank. So the analogy there was like if you were asked to find out how big the size of a room is, but you're only allowed to look at 2 of the walls at the same time and you don't know what's behind you, that's an impossible task. And that's the same for an exercise like this, that the only thing you can say about the size of the room is that what it at least is in terms of size. So that's just a thing to remember always. And if someone is telling you something else, bring them over to me and I'll take a serious chat with them. Anyways, this was great. If there's any questions that comes up after, let me know. If you want to work on some of this on your own walls, I'll be happy to do it. The last thing that I didn't mention that I get a lot of questions about that I think is also good to emphasize is, if you look at the Anadarko Basin, for instance, some basins that have very, very low or there can be an infinite acting and transitional flow for an extremely long time. So you don't get this kind of, where there's a big headroom between your DCA EURs, even if you're using something conservative, and your contacted pore volumes. Then that can be actually an indication or another tool in your toolbox. I use it all the time. Like, okay, that makes me feel better that this well is at least still infinite acting or transitional. So and I just run it quick, draw a line and say, okay, my DCA EUR with like a 0.8 B factor gives me 300 barrels for oil. And then my multiphase FMB OIP is 300 barrels. I can almost guarantee you, even without even going into analytical RTA or numerical RTA or any of these RTA techniques about flow regimes, to tell you that well is infinite acting or least transitional or very transitional. So that's another tool in your toolbox that you can use actively, even in cases where you're still infinite acting and transitional. Because I see a lot of people are like, yeah, but I can't use it because I'm still infinite acting and transitional. And I think the answer to that is, I don't think that's the case. I think there's a lot of good information you can still get out of doing it even for those wells. So that will be my last spiel for today, and we'll just stay in touch here. Let me know if there's any other questions. We're always available at support@whitson.com, and thank you all for joining.
Thanks, Matthias.